Ladies and gentlemen, good afternoon. So today I have a pleasure to present you the performance of advanced fuels in end-use sectors. Okay, so I would like to start my presentation with showing you the magnitude of the decarbonization challenge. In 2017, we used nearly 2.8 gigatons of oil equivalent in total in transport, included all fuels and electricity. When we look into the field, please take this blue field as the area that represents this 2.8 gigatons of oil equivalent. So when looking into the oil products, it covers this much area, so roughly all of the area, but we have still some place left for the natural gas, which is over here, then biofuels and waste, and electricity, including EVs, trains, and all other. So when looking into this shares, it looks like 96% of the energy use in transport are fossil fuels. So there is, so to say, no point in the competition between, for example, EVs and biofuels. In my opinion, they should go hand in hand, promoting each other to cover as much as possible of black and gray field of oil and gas products coming from the fossil sources. Because on 2050, we will have at least 4 gigatons of oil equivalent in the low case scenario. So the challenge is pretty big, and we need all solutions to go together. But the fact is that nowadays we can utilize same feedstocks to produce either electricity or fuels. So we can use even renewable electricity from wind farms to produce electrofuels. We can use waste via gasification, fission drops, and so on. So the possibilities are there. And then we can utilize this electricity and fuels, of course, to power the mobility. So in my eyes, we should not, so to say, reject technologies like internal combustion engines, and but rather focus on the feedstock to bring the real change from the environment perspective. An advanced fuel project supports the commercialization of advanced renewable energy source fuels in the transport sector, and we as Alto are the only partners responsible for the end-use part of the project. We were responsible for the task 5.4, so fuels and fuel blend properties in end-use, and more specifically, we were focusing on aviation, on-road light-duty vehicles, heavy-duty vehicles, and marine sector. In total, we developed 7 models representing the end-use performance, so how fuel properties affect engine performance over the whole fleet perspective. And we incorporated all of those models into the user-friendly tool, where you will be able to perform your simulations in, so to say, nice environment. And as an example of the models, I would like to show spark ignition models for light-duty vehicles. So the model for the regular SI fleet is above. It represents the impact of the research octane number, density, lower heating value, volume base, and oxygen content. The data are coming from various countries, different institutes, and the blacks are data from the real chases dyno runs with the new European driving cycles. The red is a model. So as we see, model is very accurate. It predicts very well the data. And what's interesting over here is that you can see that despite higher fuel consumption, volumetric fuel consumption, many alcohol blends have lower CO2 emission. And this comes from both carbon content, but also the mass-based fuel consumption, which takes into account the density. But this is the case of the regular fleet. Now the question is, what if we use same fuels in engines that are a little bit optimized, like flexi-fuel engines, that can have higher thermal efficiencies of energy conversion processes through increasing the efficient compression ratio. So here is the model that represents the effect in the flexi-fuel fleet. What's interesting is that, for example, we can see the E85 in the regular fleet that has 45 or 36, 37% higher fuel consumption than gasoline. Those two are coming from different sources, but as we see, that model predicted very well both of them. This is the difference is that some at E85 standard is pretty flexible. You can have on the upper limit of 85% of ethanol or lower limit as low as 70%. So this a little bit defines what will be your change. But in the flexi fuel fleet, we see values oscillating near 30. And the other thing is that the CO2 emissions are further lower in the flexi fuel fleet than in the regular fleet. So we see the impact of fuel properties, but also engines itself can utilize, for example, higher RON of some fuels that have this higher RON. Due to the time regimes, I was not able to show you aviation models, marine and heavy duty, but you can find them in the deliverable D55 on advancedfuel.eu website. But also, you can access our tool, online tool with a free public access after a free simple registration. You just go to advancedfuel.auto.fi and you can perform operations on the models that we developed. Now, I would like to stay a little bit on this table to show you our recommendations. What are good fuel candidates in our eyes by 2040 in various transport sectors? As you know, aviation is the most difficult to be electrified. So in aviation, synthetic paraffinic kerosene out of the Fischer-Tropsch or HEFA or ATG, alcohol to jet conversion, they look as the solution by 2040. Also synthetic isoparaffins, but they have lower blending wall, 10%. In both cases, the costs are high, significantly higher than for regular jet A1. The marine engines, we see that hydrogen is a good candidate. Now, currently, hydrogen is under research and development phase, but it is not technologically possible. Good thing about hydrogen is that it could be blended with methane. So, for example, LNG ships can use hydrogen, and blends by 20% are, so to say, compatible without big changes on the ship. Then, a good thing another about hydrogen is that there is no sulfur and no carbon. No sulfur is compatible with new IMO regulation with the sulfur cap, and no carbon is a good path to go for the marine IMO target for the carbon dioxide emissions, cap 50% by 2050. Now, methane, biogas, as a liquefied biogas could be substitution for liquefied natural gas. So the good thing about this is that there is no sulfur, and again, fleet operators will need to go either for scrubbers or for LNG or for methanol if it comes to the change after the new IMO regulations. So LPG could be a good solution out there. Now, I mentioned methanol. Methanol is possible. So, for example, case of the Stena, a commercially proven already methanol ship. Methanol could be used as a, for example, pilot-assisted mixed control combustion. And what I mean by that is that basically we inject methanol and then we inject small amount of diesel just in order to ignite the mixture, to provide the ignition source. So methanol does not have any sulfur content, which is also very good, and is cheaper than ethanol and about 50% more expensive than heavy fuel oil. Another good fuel with a little bit more future potential is biocrude from hydrothermal liquefaction. It's a promising candidate, but at the low technological readiness level, between 3 to 6, dependent on the conversion and on the feedstock. So to say, presently efficient upgrading is needed for that one. In the light duty section, we see electrification, of course, as a good way, but electrification alone will not solve the problem of the decarbonization. So the market dynamics of the every new car bought today is average fleet in 2035. We need to remember this. So in light duty vehicles, methane is also a very good solution. So for example, LBG, methanol, as proven in the China, then ethanol, currently low blending was 10%, but flexi-fuel vehicles can run on E85, and they are pretty feasible to do it. Also, HVO and FAME, as we know, widely used, and of course, and nowadays, research and development in the direction of renewable diesel. So in the heavy duty, we see that methane again is a good candidate for long haul transport, for example, in the liquefied form, in the short haul transport in the compressed form. So good thing about methane in the light duty and heavy duty is that we can convert regular fleet spark ignition and compression ignition cars into the compatible methane compatible, so to say, engines. And methanol is also possible as an MT95, which is under R&D, pretty promising. So emissions and lower NOxes than in case of ED95. But similarly to the ED95, these are dedicated engines. So both for MT95, ED95, high compression ratio engines are needed, completely dedicated. So we face also difficulties when it comes to the infra and vehicles. So thank you very much for your attention. That would be all from my side at the moment. And I warmly invite you to the discussion.
Thank you very much for that, Yuri. We did actually have one follow-up question here for you. The question is, are regular vehicles compatible with ethanol concentrations above 10%?
Well, I would say modern spark ignition vehicles could go with, technically, they could go until 15%, 1.5. But 10% is a safe limit as it is in the EN 228 standard. The problem with ethanol in higher concentration is that it accelerates the corrosion. So we need to have corrosion resistant materials, and also we lose on the performance. So when we have a little bit optimized engines that can, for example, increase the effective compression ratio by boosting the intake pressure, for example, variable valve timing or retired spark timing, it can give the bigger heat release and so to say, better effect. And of course, higher concentration ethanol can resist the knocking because of the higher RON, so we can do it from the technical perspective. But I would say 15% is top. We shouldn't try more for the regular fleet.
Okay, thank you for that very clear answer, Yuri. Thank you for your presentation as well. So we move now to our final presentation of the day.